Hi everyone, this is Professor Zucker and I'm making this video to try to really do a good job on teaching you how to prove a limit. So let's begin, but first we need to review the definition of a limit, which is to say we need to understand what we mean when we write the limit as x approaches a of f of x equals L. So way back in section, I think it was 2.1, 2.2 in fact, we studied a casual or intuitive definition of a limit. And it was like this, that the limit as x approaches a of f of x equals L means that by taking x to be sufficiently close to a, but not equal to a, we can get f of x to be arbitrarily close to L, meaning as close to L as we like. So we played around with that intuitive or casual definition, but then in section 2.4 we made it precise. So here is the precise definition of the limit. The limit as x approaches a of f of x equals L means, first in words, for every epsilon greater than 0, epsilon is just a number, so for every number epsilon greater than 0, no matter how small, there is a number delta greater than 0, so that whenever x is within delta units of a, but not equal to a, then f of x will be within epsilon units of L. So this phrase, whenever x is within delta units of a, is equivalent to the casual definition where we said when x is sufficiently close to a. And to say that f of x will be within epsilon units of L, since epsilon can be any number no matter how small, is to say that f of x will be arbitrarily close to L. Now, we can make this precise definition symbolic by saying that the limit as x approaches a of f of x equals L means that for every epsilon greater than 0, there is a delta greater than 0, such that if, this is the same thing as saying in words, x is within delta units of a, however not equal to a itself, hence the difference is strictly greater than 0, then it follows that f of x is within epsilon units of L. So with Desmos, I have a few pictures here to show you what that means. Using the function f of x equals x squared, we're actually taking a look at the limit as x approaches 2 of x squared equals 4. And in this first picture, we've taken an epsilon of 1. And we say that if epsilon were 1, then we can find a delta that works. That if in fact the delta is about 0.23, if we go 2.23 units on either side of our limit 0.2, then for every x that's within that delta interval surrounding 2, f of x will be within the epsilon interval surrounding 4. And in this case, epsilon's 1. If I shrink epsilon, make it smaller, in this case only 0.5, then that means I have to also find a new delta. And if I choose delta to be 0.12, then I find that for all x that are within 0.12 units away from 2, the f of x values will all be within 0.5 units away from 4. And lastly, if I shrink epsilon even further, make it 0.2, then that just means I have to shrink delta so that in this case it turns out that delta is 0.049 approximately. And if I am that far away from 2 on either side, all x's that are within 0.049 units away from 2 will map into the epsilon interval surrounding 4. All the f of x's will be within 0.2 units away from 4. Okay, so that's just a review of what the definition of a limit is. But now what we want to do is to prove a limit, and that was the point of this video. So to prove a limit is to show that the precise definition of the limit is satisfied. And I'll begin with this first example. Suppose we'd like to prove that the limit as x approaches 6 of the function 5 minus 1/2 x is equal to 2. Now intuitively it makes sense, because as a polynomial, if I just replace x with 6 and calculate it, it comes out 5 minus 3, which is 2. But can we prove it according to the precise definition? So here's the proof. Now I begin every proof, and I want you to do the same, with what it is we have to show. And I literally write, we must show that, now I'm stating the precise definition, for every epsilon greater than 0, there is a delta greater than 0, such that if, using the numbers up here, if x is within delta units of 6, then f of x, 5 minus 1/2 x, will be within epsilon units of 2. Now that's what we have to show. Now, I'm just pulling out of the air for the time being. I say that for any epsilon that might be named, any positive number no matter how small, simply take delta to be twice epsilon. Now you'll see in a few minutes why I've chosen that, but let's show now that choosing delta to be 2 times epsilon actually works. So we begin with the if part of our statement. Here it is. We start with that, replacing delta with our chosen delta, which is 2 times epsilon. And then we just logically follow all the way down until we draw the conclusion, this being the conclusion. And let's look at that. So if the absolute value of x minus 6 is between 0 and 2 epsilon, then I can drop the 0 is less than part and make a slightly weaker statement, but it's certainly true that the absolute value of x minus 6 is less than 2 epsilon. And if I multiply on both sides by 1/2, that'll eliminate the 2 on the right. If I bring the 1/2 inside, now I can do that only if 1/2 is a positive number, bring it inside the absolute value, multiply by inside both terms, I'll have absolute value of 1/2 x minus 3 is less than epsilon. And then, for our purposes, I'm going to actually need to take the opposite of the quantity inside the absolute values. But it is true that the absolute value of a is equal to the absolute value of the opposite of a. So by taking the opposite of this quantity, I produce this statement right here. Namely, that the absolute value of 3 minus 1/2 x is less than epsilon. And by rewriting 3 as 5 minus 2, we end up with exactly the conclusion that we wanted. Let me scroll up a little bit to show you right at the top of the screen. That's precisely what we were after. And so to draw the final statement, to end the proof, we state which was to be shown. And that's the formal end of the proof. But you're probably asking yourself, how did I know to choose delta to be 2 epsilon? The whole proof depended on it, but where did it come from? Well, that's what I call the hunt for delta. And the way it's done is I start with the conclusion. I start with the statement about epsilon, and I work backwards to try to find a connection with the absolute value of x minus 6, x minus the limit point a. So in this particular case, I started here with the conclusion. I combined 5 and minus 2. I multiplied both sides by 2. Noticed that I almost had what I needed because I was actually trying to get a statement about the absolute value of x minus 6. I actually got instead a statement about the absolute value of 6 minus x. But recognizing the properties of absolute values, the absolute value of 6 minus x is the absolute value of x minus 6. So I ended up with that, which, remember, looks remarkably like that. And that was the reason why I chose delta to be 2 epsilon. But in the formal proof, which is above this screen, I simply started with delta being 2 epsilon as if I just pulled it magically out of a hat. All right, let's do a second example. This one's more complicated. All right, in example 2, I want to prove a quadratic limit. And these are usually the more difficult ones. In some classes, certainly not in an honors class, they wouldn't even do a quadratic limit. But we're an honors class, so we're going to do a quadratic limit, and here's how it works. So the object here is to prove that the limit as x goes to negative 2 of x squared minus 3x plus 5 is in fact 15. We start out in our proof by saying exactly what it is we intend to show, which is just the definition of the limit. We must show that for every epsilon greater than 0, there is a delta greater than 0, such that if x is within delta units of negative 2, and x is not negative 2 itself, then the function x squared minus 3x plus 5 will be within epsilon units of 15. So once again, without my telling you how I got it, I'm just going to take delta for any epsilon to be the minimum, that is to say the smaller of the two numbers 1 and epsilon over 8. And I'll show you in a few minutes why I chose to do that. But having said it, now I'm just going to show you that this delta works. So let's begin. I start with my premise. If 0 is less than the absolute value of x minus negative 2 is less than delta, which we're saying is the smaller of 1 and epsilon over 8, then it will follow that. You'll notice all I did here was to rewrite x minus negative 2 as x plus 2. And since delta is the smaller of these two, then this statement here is certainly true. If delta is the smaller of 1 and epsilon over 8, well, then it's definitely smaller than 1. But it is also true, since delta is the smaller of these two, that the absolute value of x plus 2 will be smaller than epsilon over 8. So saying that delta is the smaller of 1 and epsilon over 8 actually gives us two inequalities, both of which are true. And we're going to need both of them. Going back up here. Okay. So let's take this one first. If the absolute value of x plus 2 is less than 1, then rewriting that as an inequality would give us that negative 1 is less than x plus 2, which in turn is less than 1. If I simply subtract 7 from all sides of this inequality, then I get a new inequality that says that negative 8 is less than x minus 5, which in turn is less than negative 6. Now, I can make a weaker inequality out of that by replacing this number with a larger number. And I chose to do that so that now I have a symmetric inequality, and I can rewrite it as an absolute value. So this line is weaker than that, but the next line is equivalent to the line above it. So in conclusion, at least up to this point, if the absolute value of x plus 2 is less than 1, then the absolute value of x minus 5 is less than 8. Now let's see what this is going to mean for us. Looking at the conclusion of the precise definition, I needed to show that this quantity, the absolute value of f of x minus L, I needed to show that it's less than epsilon. I'll do that right now. First I'll combine these terms in the middle to get minus 10. I'll factor that polynomial and split the factorization up into the product of two absolute values. But we already know from our analysis above that this is less than 8. So I'm saying it's less than 8. But furthermore, we also know from over here that the absolute value of x plus 2 is less than, that right there is less than epsilon over 8. And when I put those together, the 8's cancel, and lo and behold, I've demonstrated what I set out to prove. And just to summarize, in summary, if 0 is less than the absolute value of x minus negative 2, which is said to be less than delta, chosen to be the minimum of 1 and epsilon over 8, then it follows, as we just demonstrated, that the absolute value of f of x minus 15 will be less than epsilon, which was to be shown. Make sure you make that statement. So what remains is, how did I know to take delta to be the smaller of 1 and epsilon over 8? How did I know? Well, that's what I've been calling the hunt for delta. And typically we start with the conclusion. That is, we're trying to show this statement here, that the absolute value of f of x minus L is less than epsilon. So we're going to play with that conclusion until we can find a connection to the delta inequality, to the absolute value of x minus negative 2. So I start with the conclusion here. I combined terms, I factored, and so now I'm at this point. And then I make this strange leap, but I say, you know, if delta were smaller than 1, then the statement, the absolute value of x minus negative 2 would be less than 1 would be true if delta were smaller than 1. Rewriting that as an inequality, subtracting 7 from all members gives me an inequality on x minus 5. Making that inequality weaker by replacing the upper bound with a higher number gives me a symmetric inequality that I can write as an absolute value. And you can see where this is going. I hope it may take some reflection, but in time you'll see. So what we say is that if it's true then that I take delta to be 1, and if it's likewise true that delta is epsilon over 8, then the product of those two will be less than, going over here, less than 8 times epsilon over 8, which is epsilon. So to ensure that both of those inequalities hold, I just simply force delta to be the smaller of those two quantities, and that will force both of those conditions to simultaneously hold. So by taking delta to be the minimum, meaning the smaller of 1 and epsilon over 8, we ensure that both inequalities are true, and then our proof above is established. Well, I think that's all I want to say for now. We'll do more examples in class tomorrow, and thanks for listening. I'll print these notes and post them on Canvas right away.